turning,
Oh.
and then the brake pad goes down on the wheel and stops it, this gets very, very hot because all of the kinetic energy from the car goes into the brake pad as heat.
It doesn't matter.
In fact, you need to keep it cool or it will melt. Yeah. So they designed the car so that the air that comes in blows on the brake pad to cool it down. And if it didn't, it would melt. Yeah.
The car will have accident.
Quite a bad accident. Alright, let's continue with the next lesson then.
Okay.
Right, do you want to take a picture of these questions? Because I know you like to do that.
Yes.
Okay, go ahead.
Okay, 1 second.
Yeah.
I'll go get my phone.
Yeah.
I did. I'll send it to you.
No, I'll take it.
Okay.
I'll send it to you. Okay.
Do you want to take a picture or you'll use Moodle? Yeah, I think this is better. I don't know why they do this.
To waste time.
What?
Maybe. Okay, now we can close this. Right. So the most important thing about this lesson is the conservation of energy. That the kinetic and the potential at the start equals the kinetic and potential at the end. Okay.
Like you mean the transfer of energy?
The transfer of energy, yeah. Okay, let's have a look at the next lesson.
Okay.
So this is already lesson 19, or topic 19, power and efficiency. Okay.
Okay.
Some of these words maybe you know already, like power.
But I forgot it all.
That's okay, you'll see them again. Okay. You're doing okay? Do you have something here?
Yeah, I have a headache.
Does it help?
Yeah.
Yeah? Okay, good. Right. Right, so I want you to imagine this. You carry 1 kilogram up a hill. So if you have no imagination, which some of you don't, I'll draw it for you. So you have 1 kilogram here, and you carry that up a hill, and there's 1 kilogram up here. Okay? And then the second, now imagine 1,000 ants. The ants are the small
the
insects.
black one.
Yes, or brown. And they each carry 1 gram up a hill. So you have an ant, and then it takes up 1 gram.
Of what?
It doesn't matter. It doesn't matter.
No, like.
It does, quiet. Right. And then it takes up another gram. So now it's 0.001. And it does this 1,000 times. So in total, how much is up here? Also 1 kilogram. So my question is, on top of the hill, you have 2 piles. 1 kilogram from you, and 1 kilogram from the ants. Right, who did more work? Ants are small insects. Yeah. Who did more work?
Same.
Same, very good. Same. Because in both cases the work done was potential energy, which equals mgh. Are the m's the same? Yeah.
Yes.
1 and 1. Is g the same?
Yes.
And is h the same?
Yes.
So the work done is the same.
Yes.
But this feels wrong because in our mind we think the ants do more work.
Are more.
Yeah. So this is because
the mass is equal to, why is the mass is equal?
because the ants moved 1 gram 1,000 times. So in total it makes 1,000 grams, which is 1 kilogram. Yeah. So although it's the same work, something about the ants seems wrong. Yeah. And that's because it's important to know how quickly something is done. And this gives us the idea of power. So if you do some work quickly, that's a lot of power.
Yes.
And if you do some work slowly, that's a little power. So power is the work done per time. So as a formula, power is the work divided by the time. This is the power. Yeah, so write this down. Okay, do you have this, Adnan?
Yes.
You wrote this down? Yeah. So, what would be the unit?
Joule per second.
Joule per second. Can you see that? Joule per second. So the units are, of course, joules per second. However, we have a special name for joules per second. It's also called a watt. A W, a watt. So 1 watt of power is 1 joule of work done in 1 second. That's the definition of a watt. Yeah, it's 1 joule of work done in 1 second. And you might know this because we talk about the light as like 60 watts or 100 watts. Oh yeah, speakers, yeah. What are they, like 10 watts? What would be good speakers?
I have one that 40.
Yeah, they're bigger ones. Yeah. Okay, do you have this as well? Yeah. Continue? Yes. So you can use watts or joules per second. Yeah. Okay. So when you convert electrical energy into light energy, you have not used any energy, you just converted it. But, so when the electrical energy becomes light energy, not all of it becomes light. Some of this electrical energy becomes light, but some of it becomes heat. Yeah. So you want the light, but you don't want the heat. The heat you don't want. So here's my question. In fact, if you have a 100 watt bulb, that means 100 joules per second. How many joules do you think will be light, and how many joules do you think will be heat? In your opinion. So this light, so you would say 70 joules is light, and 30 joules per second is heat. Anyone else? What do you think?
80.
You think 80 joules are light and 20 joules per second heat. What do you think? 94.
90.
Yeah, but 94 light and 10 for heat.
Oh, well, it depends.
It
Light.
Let's say an old light bulb.
Or
Yeah, but
maybe
the yellow
sometimes
ones
it's only.
The orange lights are more.
I know it's different. Let me draw it. I'm talking just a good old fashioned.
It seems like the wire takes more energy.
This is a bad picture. No, I'm just talking about good old fashioned light bulb.
75.
80.
So you're saying light and heat, you're going with 75, 25. Yeah, and I think you said 90,
I'll go with 50.
50, okay. Anyone else?
70-30.
You're going 70, 30,
90-10.
90, 10,
80-20.
80, 20. Okay, anyone else? No? Okay.
Say all of them.
All wrong. All wrong. The true answer is, ready? 199.
How?
That's what it is. Yeah.
Oh, it's old.
For an old light bulb. Yeah, that's it. You'll get 1 joule of light and 99 joules of heat per second for an old light bulb.
I was like, what?
It's actually, yeah, you're very close. Yeah. So you can see that a lot of energy is wasted as heat. You don't want this. You only want this. Now the new light bulbs will be much better than this, of course. Much better than this. But like the LED lights, yeah. But for the old light bulbs, it's like this.
What does the light have to do with the heat in the wire?
So the way that the light is made is the current is passed through this element here. And what happens is it glows. And the glowing makes light, but also it makes heat at the same time. And you want the light part, but you don't want it to make the heat part. So LEDs make more light than heat. Yeah.
Whenever you touch a bulb with
It's very hot. It's very, very hot.
Low resistance.
High resistance means more heat.
Yeah, low
Yeah.
resistance for the LED.
Oh yeah, lower resistance, yeah. Okay, so this gives us the idea of wasted energy. Okay, so was it 50-50, maybe more, maybe less? In fact, 1 watt of light and then 99 watts of heat. So this gives us the idea of what's called efficiency. Efficiency is how much energy is useful and how much energy is wasted. So as a definition, efficiency is a percentage. So here, look, wait. What you're saying here, when he said 50-50, he's saying 50% of the energy is useful. Or here, when you say 75-25, you're saying 75% is useful. But really, how much is useful?
1.
Only 1%. So efficiency is a percentage. It's the percentage of useful compared to the input.
Yeah.
So as a formula, efficiency is useful over total times 100%. That is a lot of apple juice.
No, it's not apple juice.
It says apple on it.
Yeah, but it's just water.
That's water?
No, it's tea.
Oh, okay, alright. Yeah. Yeah, does anyone know this letter? It's a Greek letter.
Mu.
Mu? No. Nu? No. Alpha, beta, gamma? No.
No, I know it's
Neon.
Mu? No.
it's like this mu something.
No. Theta? No. Pi? No. Epsilon? No.
What?
No.
Sigma? No.
Epsilon is E naught.
Yeah. Yeah.
Epsilon is in German.
Epsilon is
It's also
E naught.
German for the Y, isn't it? Yeah. This one, what'd you say?
Mu.
No. This letter is called
You're resisting.
eta.
What?
ETA.
Yeah.
Eta. Eta.
How can I write that?
Oh yeah. This is efficiency here. And it's Greek letter eta. Yeah.
We can also write input to output into input energy. It's called efficiency.
What do you mean?
Like it's written useful output energy upon.
Oh yeah, you can just write output over input. Yeah. So you can use it like this, or if you want, you can do it using the work. It's the same thing. You just divide by time. So you can, well actually we'll get to that in a moment. Alright, do you have this formula?
No.
Oh, okay. Yeah? Continue? Yeah. So, what do you want eta to equal? What percent?
100.
You want it to be 100%, don't you? This is a perfect world. So, in a perfect world, you want eta to be 100%. But, because of heat loss, it will never be 100. It'll be less than 100.
Yeah.
Also, if we divide it above and below by T, we can make this formula, which is the same. You can use useful output power over total input power. So you can use energy or you can use power. You get the same answer. Okay, because if you think about it, look here, eta equals work out over work in times 100. Yes? But if you divide the top by T and the bottom by T, what do you get on the top? Work divided by time?
Power.
Power. So power out over power in. So you can use work or power for this formula. So if you can just make note of that. You don't have to write this again. You can just say, if you want power works, no, not power works. You can use power instead if you want. Yeah. Do you use the same letter back home for efficiency? Use E. Yeah.
Capital E.
Yeah, but I use that for energy. Does anyone else use this letter back home for efficiency?
No.
No? Okay, continue. Yep. Right. Let's see. So we have a couple of questions, yeah. So a boy lifts a 2 kilogram physics book off the ground, a height 1.1 meter. It takes him 2 seconds to do this. Okay, I want you to try this. I think you can do this. I want you to calculate his power. So try this question. See if you can do it.
1.1 power.
2 multiplied by 1.1 over 6.
Yeah.
Yeah.
So 1.2.
So it will be
It's mgh. Yeah, because think about this. What does he do? He takes a book, which is on the ground, and he lifts it up here. So here, what's the kinetic energy? Zero. And the potential energy? Zero. So here it has zero energy. Kinetic? No. Potential? Yeah, what is it? mgh. So this came from the boy. It was zero and now it's not zero. So that means the boy did the work. So the work that the boy did is equal to mgh. What's the m? 2. The g? 9.8. And the h? 1.1. So what's this? About 20, is it? 21.5 joules of work. Do we want work? No, we want power. So what is the formula for power? Work over time. And what did I say the time was?
2 seconds.
2. So this is 10.8, was it? Okay. Well, if I do 21.5 divided by 2, I get 10.75, yeah. 10.8. And the unit for power?
What?
Watts. What's wrong, Mir? You don't look happy with this.
No, I did it wrong.
Okay, well that's okay. We can write it down this way.
Okay then.
this is easy.
Okay, we'll do the B part in a moment. Part 2 in a moment. So this is part 1.
How did you get 1.1?
That wasn't the question.
No, sorry, I'm talking to them.
Oh,
Yeah, I got it like I done it wrong.
No, yeah, what did you do?
2 multiplied by 1.1
I
divided
thought
by
that the 2 kg is the
Is the S?
F into D. Work formula is F into D. If we do it by that.
well actually, yeah, you could do it that way. Work equals force multiplied distance. What's the force? The force is the weight,
Yeah,
mg.
which is m, g, and s.
Yeah, S is the distance and height.
Yeah, so that's m, g, so it's exactly the same.
Yeah. I didn't put 9.81.
Yeah.
That was
You used mass instead of weight.
Yeah.
Yeah. Yeah. Okay. Did you write this down? Yeah, okay. Can I go back to the question? Try the second part. He got his energy from his breakfast. However, half the energy is wasted as heat. What is his power now?
Okay, so how he got the heat?
From his body. So, when you eat food, you can do work, but energy is wasted in making heat from your body.
How much energy for?
21.
10.8 watts was his power.
Divided by 2.
Write it down, write it down.
The power?
I want to know, you see, in the first part, we assume he is 100% efficient, that no energy is wasted. So I want you now to make it more realistic. Half the energy is wasted as heat. Now, what is his power? That's what I want you to do.
Two point seven.
No.
5.4 divided by 2.
No.
Zero.
No. No.
No, it is
Oh, guys,
We
you're...
are finished. We are
I know, I can see that, yeah.
0.5.
Right, watch. Efficiency, what did I say it equals in the question?
Output into.
No, in the question, what did I say it was? Half, so what percentage is that? 50%. Okay? The formula is power out over power in times 100%. That equals 50%. Okay? So power out over power in, that equals 50% over 100%, which equals 0.5 or a half. Now, what do we know? Do we know power out or do we know power in?
Power
Oh,
up.
We know power out,
10.6
10.75 or whatever.
Yeah.
10.8.
Yeah.
That's how much work comes out from his job.
How does 10.8 change?
That was the previous one.
Oh.
So, 10.8 is how much work he does.
Yes.
I mean, when you lift the book up, that's how much work he does. But he needs more energy than this to do it, because he wastes energy. So we don't know the input from him. So, just a quick divide. 10.8 divided by 0.5 equals the power in. No, I think it'll be like 21.5 about.
Yeah, 21.6.
21.6 watts. So, listen, he has a power of 21.6 watts, but he wastes half of it for heat, and the other half does the job. Okay, we'll do another question.
It's the same as.
Yeah, it is, because the time was 2. That's just, again, coincidence. Yeah. Okay, continue?
Yeah.
Right. Okay, this one now, I really want you to try and get this one, because you need to get one. So I'll give you a minute to try this one. A 1,200 kilogram car starts at rest and reaches a speed of 100 kilometers an hour in 10 seconds. If the car was 100% efficient, that's not real, of course,
Ideally.
then what is the power of the engine? Okay, try this one. Try this one. There's no need to ask me anything. All the information is there. Okay, do we have an answer for the first part yet?
No.
Mm-hmm. Andy, do you have an answer for the first part? Okay, can I?
Yeah, I got
Yep.
that. Yeah.
No.
But I think
I got it. Maybe it's 200.
Write it down. Did you write it down?
Yes.
Okay.
I think I have it.
Okay, let's have a look. Right, so here's the car, and at the beginning it's at rest, so the energy it has is 0. At the end, what's the speed? 100 kilometers per hour, isn't it? Now we need to change that into meters per second. What did you get for that?
27.7.
That's 27.78 meters per second. What's the mass of the car?
1,200.
So at the end it has kinetic energy, which equals a half mv squared. So the energy at the end equals, square this and then times 600. So it's a pretty big number, isn't it? 4,629,63, roughly. I know, rounding off and so on. So look, please. The energy at the start was 0, and the energy at the end was this much. Where did that energy come from? It came from where?
Burning fuel.
Yeah, the engine, basically. So this came from the engine. So what did the work in this question? The engine.
Yeah.
So the work that was done was by the engine, which should equal 4,629,63 joules.
Divided by 10.
And now we need the power. So the power is the work divided by the time. So that would be 4,629,6.3 watts.
I didn't round up, but
You know, it doesn't matter, I'll round off now.
yeah.
So that will be 46.3 kilowatts. That's the power of the engine. Now that's powerful. That's 46 kilowatts. There's nothing inside your home that would be near this. The closest thing to this would be an electric shower. An electric shower would be about 9 kilowatts. Electric shower? Well, you know what a shower is.
Yeah.
Electric shower means the electricity heats the water.
Yeah.
Oh.
Yeah.
Like you will get
I
like
will-
that.
No, you won't get electrocuted. No, not if it's done right. An electric shower is 9 kilowatts. An electric oven is maybe about, I don't know. I know, maybe it's about the same, 8, 9 kilowatts. Washing machine and a dryer, maybe they're about 3 kilowatts. What else would be high? The vacuum cleaner, maybe that's half a kilowatt.
Refrigerator.
It's annoying.
They're actually quite low. They'd only be about 100 watts. Refrigerator maybe 200-300 watts. Quite low. TV maybe about 100 watts.
Heating.
Heating, electric heater will be about 3 kilowatts.
Yeah.
Yeah. By the way, in your home, what is the most efficient item? In your home, what is the thing that is nearest to 100% in your home?
I'd say the heater.
The electric heater.
Because we take the energy to transfer to heat energy.
Yeah. So,
So no energy is wasted.
yeah. Well, a tiny bit's wasted. Does anyone know what energy is wasted in an electric heater? It's nearly 100%, but it's not 100%.
It's more.
Oh goodness, no. No.
I don't know.
If you listen carefully, the electric heater makes a small buzzing sound.
Yeah.
This sound is wasted energy, because you don't need the heater to make sound, you just need it to make heat. So if you listen, you can hear the electric heater, and it makes a humming sound. This is wasted energy. So electric heater would be nearly 100%, and what would be nearly 0%? What would be at the other end? Well, the light would be nearly 0, and the electric heater, we don't have one, is near 100%. What about a TV? What do you think?
It's I think 70-30.
Maybe
Because it's not that it doesn't emit so much.
I think a
I say
TV.
90.
Yeah.
No, I don't think it's that high. I think it'd be,
70.
well, it depends on the TV. Are we talking about a new TV?
Yeah, like
Okay.
one flat.
Yeah, okay, that'd be about 90.
Yeah.
A smart TV would be about 90, yeah. What about a PC, computer?
You see, it's annoying.
Yeah, what about,
It emits heat.
it does, so what percentage would you say, a computer?
70.
No.
80.
Less?
50.
I think it's less
25.
than 1%.
What?
The computer part, now not the screen, the computer,
The keyboard.
like the processor. Yeah.
There's too much heat.
There's too much heat, like, I mean, the heat is
Yes, it comes.
coming out here.
And it's hot.
Yeah, the processing, like saving the file, reading the disk. This would be less than 1%. Most of it, you can feel it, most of it is heat coming out the side. And you can feel it when it's on your lap. It gets very hot. So less than 1%. It's even worse than the light bulb.
It's annoying when it's hot and
It is annoying. Yeah. Alright, now try the next part. Of course, no car is 100%. This is not realistic, okay? Most cars are 40%. Where is the wasted energy here in the car?
the 40%.
Yeah, where is the
From the
heat? What part of the car gets hot?
The
engine.
The engine. The front of the car. It gets warm. Yeah. Okay, try it now. What's the power if it's 40% efficient? Try that.
So,
Try that. It's like the last one I did, yeah? You haven't finished?
What resistance is in the...
In A, it's 100% efficient. No energy is wasted. In B, only 40% of the energy is useful and 60% is wasted.
I think it's 1852.
or maybe it's
Shh. Just do it.
1852.
I got 185 0.
Yeah.
Yeah, that sounds about right, yeah. So, what's the efficiency equals 40% times 100% equals 40%. So which do I know, the in or the out? I know the out. So that's, what was it? My goodness. 46296.3. And the input? I don't know. That's what I want. Yeah? So, let's see. If I just rearrange this, I get 46296.3 times 100% over 40% equals power in, which equals, what you said, 2.5 or something, isn't it?
No, 2.5 is 100.
Oh, okay, I see. 296.3. So we get, and I put in kilo to make it easier to read. What did you say?
Well, I didn't convert it to kilo.
Doesn't matter.
1852.
18508, but I didn't.
I got 116. What did you say? 105?
Yeah.
But-
185.
Yeah.
185?
Yes, yes.
Oh, maybe I did something wrong. Sorry. Let me
No,
check.
it's
I'm right?
116.
Yeah. 116. Now, if it's a bit different, it's because of rounded. Did you do it the same way as this?
No,
Yeah.
we have different values than the power.
Yeah. Oh, yeah, because of
No,
rounded
I got
speed.
1150.
Okay,
Yeah.
great.
There it is.
116 kilowatts is the energy from the power from the engine. So if you think about it like this, what's happening, if I draw the car, this is the engine. The engine has a power of 116 kilowatts. How much of it makes it move? Only 46.3 kilowatts. Where does the rest go? Off as heat. How much heat? 116 minus 46.3, that is 69.7. So, look here. 116 kilowatts is the power of the engine. Only 46.3 is useful work to make the car move. The rest, 69.7, is wasted as heat. Now, not all of it is actually wasted. Does anybody know where some of this goes? Not all of this is wasted.
Like the rest of
Heated.
the car.
Into the
Yeah.
battery.
Some of this goes back into the car to heat it.
Like air conditioning.
Like air conditioning, yeah.
Yeah.
So I mean, it's not all wasted, but most of it is wasted.
Still a lot.
It's a lot, isn't it?
Compared to the-
It's a lot. So, you know, think about this. When you spend, if you spend 116 euros to fill up your car, 70 euros is wasted and 46 euros is used to actually get you from here to here. Now, when you think about it like this with money, all of a sudden it matters more to you.
Yes, yes.
Yeah?
There are many, like, matter.
Okay, what if I change,
Yeah.
if I change the fuel itself, like if I use different.
Yeah.
Doesn't matter.
This 40% is not because of the fuel. It's because of the
wires.
well, because of the engine, how the engine is designed. So changing the fuel doesn't really improve this. You can improve it by maybe 1% by using a more expensive fuel. But really the problem is the engine, because as you know, maybe the fuel explodes, and when it explodes, pushes the piston to move. But of course, when something explodes, that makes heat. And it's very difficult to have something explode and not be hot, okay? So the problem is with the, it's just the whole concept. Until you have electric cars, the best that you could probably make this, I can't imagine this being more than 50%. Like,
Even like Ferrari, Formula One, maybe.
yeah.
More than 50.
Can it be more than, I don't think so. I don't think so, because at the end of the day, you're going to need it to explode to move the piston. And like I said, it's hard to imagine an explosion that's not hot, you know. You could maybe use different fuels that don't get as hot when they explode. Maybe 50, maybe 60, but still, I think 40 is actually pretty good. Like 40 might be a small car, something like an SUV. You know SUVs? Yeah, they can make like 25%, 20%. You know.
Buying a new engine, which is like more efficient, would cost less with the fuel.
I think you save your. I think you do save your money if you get a more efficient over like 10 years of the car. Yeah, I think it is worth it to get more efficient car. Yeah, and in fact, now that we're talking about this is what your coursework, your physics essay is going to be about. You're going to write an essay about efficiency of cars, and in particular, something called a hybrid car. You know a hybrid car.
Engine and fuel engine.
Yeah. Yeah. Your physics essay, which you will have to write, will be about cars.
That's nice.
Yeah, and it'll be in particular about hybrid cars, which are the electric and the petrol engine together. Yeah.
Like BMW i8,
Why?
the hybrid.
But hybrids are great.
Yeah, it's like 3 cylinders, the other engine, the fuel engine can reach like 200 kilometers per hour.
So why do you hate it?
No, I don't hate it. It's such a nice car.
Didn't you say I hate BMWs?
No,
Okay,
why would
okay.
I say that?
I could have sworn that's what I heard. What did you? Oh, it's fine, fine, fine. What did you say?
I said like the BMW i8.
Hey.
One number 8.
Okay, all right, right, all right.
I,
The i8
yeah.
BMW.
Yeah,
Right, okay.
yeah.
No, I hate BMW. Okay, all right. Yeah, so this is good. You can talk about this stuff in your essay about how efficient it is and how much it costs, you know,
Yeah, it's expensive.
the benefits and the disadvantages, all this stuff.
We can make a nuclear car.
When you really think about it.
Nuclear car. No.
Yeah, why not?
Physics essay.
Nuclear
Nuc-
radiation.
No, originally people thought this could be possible, and it could still be possible. The problem is, it's too difficult to make the engine
hard.
small.
It's
For-
hard to do
Wait, what?
nuclear car.
He wants to know, could you have a nuclear-powered car?
Yeah, why not?
Because you can't make the engine small enough to fit in the car,
Yes.
because you need a lot of
It-
equipment.
Okay.
I mean, the idea is possible. Like, there's no reason you can't. The reason you really can't is practical. I think you can't make it miniature. It's too difficult because you need a lot of stuff to do it. Okay, let's have a look here now. So here are your questions. If you want to take the picture, please.
We will not take it.
You will not take it this time.
Because so bad.
Okay.
You're so trying to take pictures.
Okay.
I send it to the book.
No, I will do it from I've got one more practice.
This early homework.
This one and the previous one.
The previous one is just one question left.
Yeah, most probably.
There's just one or two questions left from the other one.
One is left for me. I have
Yeah, we number 5. Yeah.
Oh, you did number 4.
We did number 4.
Okay.
number 4, number 5. Only one is left. 6.
Okay, fine. That's fine. That's fine. And then you have these, but these are quite short because they're just percentages to calculate.
That's an easy one.
Yeah, it's an easy one. Yeah. Okay, we'll finish there. So.
Compared to the 3 short and all that stuff.
Well, now